Well, thank you very much for that introduction. It's certainly a pleasure to be here. Now, I want to talk about things which are in my latest book, Shadows of the Mind, but most of what I want to say will be on these transparencies, and I suppose I should discover how to turn the lights down. I don't know if I can do that. Perhaps it can be down there. Thank you. I want to address the question of the relationship between conscious thinking and computation. Now, I can think of about 4 different points of view that one might hold on this issue, and I've listed them here. The first of them is what I'm calling point of view A, which is that all thinking is computation, and in particular, feelings of conscious awareness, let's say, any feeling that you have, consciousness, any manifestation of mentality, is merely a feature of the carrying out of a computation. So a computer, appropriately programmed, and I have here on this gadget, if I can get this one going, right? No, not right. There we are. I have a picture of a robot, and you can see this robot is controlled by a computer. That's meant to be a computer up there, and a human being, and they're performing some task. And according to point of view A, not only could a computer simulate the action of a brain, it might be very complicated, but in principle it could. It would also have any kind of conscious feelings that a human being would have while carrying out those computations that the computer is simulating. So that's point of view A. Now, another point of view here is what I'm calling B, which is that although you could simulate any action of the brain, and so the robot would perform acts just as well as a human being, perhaps better, but at least anything that a human being could do, the robot, in principle, if you got a clever enough program and a good enough computer, it could imitate the behavior of the human being. But that imitation, that simulation of the activity of the brain, or whatever it might be doing, would not evoke any feelings of awareness. It wouldn't feel anything. It wouldn't be conscious. So that's the distinction between A and B here. Point of view A is sometimes referred to as strong AI, strong artificial intelligence. Sometimes the word functionalism is used to describe point of view A. Point of view B is more in line with what I think John Searle has often, a point of view he's often stressed, although I'm not quite sure that he would hold to this view now. Let me indicate another view that is essentially what I believe myself, which is that there are things that in principle the computer could not even simulate in human activity. Well, you see, certain types of mental activity are things which are not even possible to simulate at all on a computer. At least in principle. There might be, in practice, you might get it could get away with it for a while maybe, but there would be things that it couldn't do. You could also argue for what I'm calling point of view D, which is that it's wrong to think about these issues in scientific terms at all, and that there is something about the mind which cannot be explained in scientific terms. According to C, I'm saying that although you couldn't simulate the action of whatever's going on in the brain, you could at least understand it in scientific terms. And I want to try and explain that they're not the same thing. I think people get the feeling that, if you can understand something in scientific terms, then in principle you ought to be able to simulate it computationally. But I'm trying to say that that's not necessarily the case. Well, let me put this over here, and I hope I can get them all on. It will. Whoops, it's going to slip, isn't it? So we're going to have problems. I think it's all right. Whoops, it's not. I'll put this here. That'll be all right, I think. Yes. Well, we now know that many things can be done very well by computers. In fact, one of the most successful areas of artificial intelligence is playing chess. Computers are now so good that they can beat all but the very best of human players. However, you could argue, I think, that whatever they're doing when they play chess, they don't understand the game. And I want to try and persuade you that this may well be the case by showing you an example here of a chess position. Now, I'm not a great chess player, as probably experts in the game will know, because I've got the the squares colored in the wrong way around. I didn't realize which way around they were when I made this picture, but you see, you don't have to be very good at chess to grasp the point of what I'm trying to say here. This is a position in which white is to play and draw. White, of course, is green here. The green king, you see, first of all, black has a tremendous advantage. There's an extra rook here, another extra rook, and an extra bishop. 2 rooks and a bishop ahead, black is. But there's this barrier of pawns here, so it's very easy for green to avoid defeat by simply wandering around here, making sure the barrier of pawns is left intact, and there is no possible way of losing the game because these pieces are just trapped behind the barrier. However, you see, it's easy for humans, but when this was shown to, well, any computer, in fact, Deep Thought, the most powerful computer of its day, what did it do? It immediately took the rook with its pawn, opening up the barrier of pawns to achieve a hopelessly lost position. Well, you see, I think it's a very nice example. I saw this about 1.5 years ago in the New Scientist in an article by David Norwood and Jane Seymour. I think the problem was made up by William Hartston. As a sort of illustration that although computers do play chess extremely well, what they do is very different from what human beings do. And I think you could argue that they simply don't understand the game at all. They certainly don't understand that this barrier of pawns could prevent these extra pieces from getting across here. All the computers do is to compute move after move after move after move after move to a certain depth, and since they can't go right to the end, they then have to make some assessment as to whether the position is improved at all, and, well, if it's taken the rook, that counts as a little bit better to the computer. Well, you see, you might say, all right, we know that. Now we understand about pawn barriers. We could make that computer recognize a pawn barrier. Say, if you see a pawn barrier, watch out, and so and so. Well, then you give it this one, you see. It's the same. Green is to play and draw. You have a little gap here in the pawn barrier, and there's a bishop here instead of a pawn. Now, there's a great temptation, of course, to take the rook with that bishop, but what you should do is plant it in there, pretend it's a pawn, and you're back with the other position. So once the computer has been told about pawn barriers, you just give it that one. And, of course, instantly, they always take the rook. Well, I think this is a good example to show you that whatever computers do, they don't understand chess. They play very well. They play certainly better than I do. But they do something different from what we do. That's all I'm trying to say, is that understanding is something which is different from computation. And that's really the main point I want to get across. But of course, if you just do it with chess, the trouble is there that once the computers do get so powerful, maybe, that they can work the game right out from the beginning to the end, then it wouldn't matter that they didn't understand the game. They just would work it right out to the bitter end, and then they would know not to take the rook. So, in a way, chess isn't going to tell us conclusively that there are things that computers can't do merely by computation. And that's the trouble, is because chess is a finite game. So one has to, if you want to make a clearer argument, you have to turn to things which are not necessarily finite. And what one has to turn to is the famous Gödel theorem. Now, I'm not going to tell you what it is in detail. I'm just going to describe what it does for you. And what one can conclude from the Gödel theorem is that mathematicians, when they do their mathematics, do not use a knowably sound algorithmic procedure. When I say algorithmic procedure, what's making that noise? Something I'm doing, perhaps? Algorithmic procedure, I mean what a computer does. That's all I really mean. To ascertain mathematical truth. And one can restrict attention to very specific types of sentence, like what the famous Fermat's last theorem. Now, I'm not going to go into what these things are at all, but let me just tell you a little bit more what it actually, what the thing does for you. What Gödel's theorem tells us is that if you're given any algorithmic procedure, that is any kind of computational procedure, then what Gödel shows is how to exhibit an arithmetical proposition whose truth can be seen to be a consequence of the soundness, the correctness of that procedure, yet it does not follow from the application of the procedure itself. It's a very subtle and clever thing. So that you see, if you believe the procedure works, that very belief carries you beyond the procedure. So that's, and from this you can deduce this. Well, you see, you can try to wriggle out of it in various ways, as people indeed do, and you might say, well, perhaps mathematicians use unconsciously some algorithmic procedure that they cannot know to be correct, and so on and so forth. Well, I should say more or less the first half of Shadows of the Mind is concerned with addressing arguments to do with this, and I'm certainly not going to go into these things here. All I'm going to do is show you a couple of cartoons. First of all, this is in relation to the issue of, you see, suppose there was an algorithmic procedure of the nature of something which is sort of unknowable or unknowably sound or something like that. How could it have arisen? Well, you might say by natural selection. And what I've got there is a cartoon which shows that whatever natural selection does, it doesn't select for mathematicians. You see, here we have a mathematician who's about to be eaten by this saber-toothed tiger, and he's well, you see, it's not very different these days. Whereas his colleagues over here, one of them has thought of how to design a mammoth trap, another has learned how to grow crops, another one to domesticate animals, build shelters, all sorts of things like that, which are no doubt what the things that were selected for. So what I'm trying to say is that the general quality of understanding, yes, that is something no doubt that was favored by natural selection, but a specific ability to do mathematics, which would be the sort of thing that you'd run up to in this argument, is not what is favored. It's just a sort of, an ability to do mathematics is just application of the quality of understanding in a rather refined context, but it's really not essentially different from other kinds of understanding. Well, you might worry about that, but it seems to me that of course, you have to be, it's understanding which is in a very kind of rigorous kind of context. Another way you might imagine is that these, you might build robots which could achieve this unknowable algorithm in some form. And I have here another cartoon. These are both cartoons taken from my book here. This is illustrating a little story I have where this chap here and his colleagues have set in train many years earlier some procedures which have finally led to this wonderful robot which can do wonderful mathematics, and they have this discussion. And, well, I won't tell you what happens at the end of the discussion. You can buy the book for that, I think. But anyway, I just want to say that these arguments are things which are gone into rather thoroughly in the book. If you disagree with them, at least I hope you read them. It's something that one has to go into rather carefully. Well, there's another way of putting this, which is that what Gödel tells us is that there is no system of computational rules that can characterize the properties of the natural numbers. What are the natural numbers? Well, they're just the ordinary numbers 1, 2, 3, 4. Well, I'm going to include 0 too. 0, 1, 2, 3, 4, etc. And you can show that there are always, given a set of rules, there are sort of funny kinds of numbers which satisfy them, which are not natural numbers, and then they don't satisfy the Gödel thing. Well, let me not go into that. The point I want to say is that rules, you see, cannot characterize the natural numbers, but if you show a child sort of oranges and apples and things like that, they can abstract from this the idea of 0, 1, 2, 3, 4, etc. And you haven't shown them a million oranges, you haven't shown them that there are an infinite number of these numbers, but yet you get the idea that these things, what they actually mean, you see, and that they continue indefinitely. And this is something that you cannot characterize by any finite set of computational rules. Nevertheless, there is some kind of understanding of the notion of what these natural numbers are that can be conveyed to a child. And I'm taking this as some sort of contact with a Platonic absolute of these numbers, you see, are things which have some kind of existence which is independent of ourselves. I'll come back to that at the end of the talk, but it's not so important for what I want to say here. Okay, now, let's not then worry about the details of all that. What I want to say is that mathematical understanding, whatever it is something beyond computation. Now, of course, mathematical understanding is a very particular kind of activity, and it may not be that interesting to most of us here, I don't know. But what I'm trying to say is that there is no clear line to be drawn between mathematical understanding and understanding generally. In fact, the cartoon that I showed you is really illustrating this point. I also want to say that I don't want to draw a line between human consciousness generally and human understanding. I mean, there are many things in the word consciousness incorporates many other concepts, like the feeling of pain, for instance. You have to be conscious of that, or the perception of the color red or something like that. All these things are aspects of consciousness. And these are different kinds of aspects of consciousness, but I'm just saying here, understanding, well, first of all, we see mathematical understanding seems to be non-computational. I'm trying to say that if this is, why should we draw a line here, here, or even here? It seems to me that there's enough in common between the way animals are, at least many animals, I don't know about all animals, and human beings, that I wouldn't like to draw a line between any of these things. It seems to me, although it's of course obviously not a logical deduction, but it seems to me if mathematical understanding involves something beyond computation, then this must be a feature of consciousness generally, including animal consciousness. Now, you see, that's what I'm saying here. If non-computability in some aspect of consciousness, for example, mathematical understanding, strongly suggests that non-computability should be a feature of all consciousness. And if you take point of view C as opposed to D, which is to say, if you believe that you can explain these things in scientific terms in some way, then this implies that there must be something, I haven't mastered this, I'm afraid, I'm walking over the cord. There must be something in the physical laws. You see, our brains are physical objects, and so if you take the view that everything in the behavior of the brain is something that could be understood in terms of the physical laws ultimately, although we may be a very long way from that, then it tells us that there must be something that you could not even in principle simulate on a computer in the way the brain works, and therefore in the way the physical laws work. Now, you might say that's a tall order. But let me first of all try to explain what I mean a little bit more than that. You see, you might think, as I said before, that any kind of scientific explanation, any kind of model, mathematical model, would be something that you could in principle put on a computer. I want to give you a mathematical model of a universe which cannot be simulated computationally. So it's the sort of thing physicists do when they can't do anything, haven't got anything better to do, which is to make a toy model of something or other. And this indeed is a toy model which is perhaps a little bit more ridiculous than most of the models that one sees, but I don't know if it's all that much more ridiculous. This model has a discrete time. It sort of goes 1, 2, 3, 4, etc. like that. Starts at 0. And the state of the universe at any one time is given by a polyomino set. Well, what's that? A polyomino set, that means a set of squares sort of joined together, like I've given some examples here. And they sort of jigsaw puzzle pieces made up out of squares joined together. And you might have several of them in the set. And you list them in some numerical ordering like this. Now, I've numbered these. I mean, I've actually made up the numbers more or less at random, but not quite. The numbering has to be such that, this is just a technical point, such that if the total number of squares here is odd, then the number there is odd. If the total number of squares is even, the number there is even. That's just a technical point. Now, how does this universe evolve? Well, it starts off at this one, the sort of empty set, and then you have a rule that if the state at time n, or time t is one of these things, Sn say, then it goes on to the next one if you can cover the plane, if you can tile the plane with that set then it goes on to the next one. If you cannot tile a plane with that set, it skips one and goes on to the next but one. I want to give you some examples here of tilings, just to show you what I mean here. Here is, here are sets of tiles. You can play around with these things. This, well, it's meant to be that way around, not that it really matters. This cross shape here, you see, you can see that that's going to go on forever. Likewise, this shape, you have them fitting together, a little bit more complicated, and that will go on forever. Now, if I took this shape by itself, no matter how you fit it together, there will always be a gap somewhere. And if I take that shape by itself, there's always going to be a gap somewhere. But if I had the two together, then I can, by continuing this pattern, tile the entire plane. Here's another one with a single shape, which will tile the entire plane. I've just given you this to show it's a little bit complicated sometimes. In fact, it takes a little bit to see where this pattern starts repeating. Indeed, it does start repeating. I won't point it out. Perhaps you can see from that thing. But anyway, that's not good enough. If you want to look at one, look at this one here. You see this set of tiles, these three, I'll tell you, they will tile the plane. But, in fact, that's how you do it. And you do it, you sort of continue like that. Well, what does that mean? You see, if you have a good look at that, in fact, I should leave that one on, I think, and challenge anyone to see how that does continue. This, in fact, is this set here. In fact, that set of three polyominoes, although it will tile the plane, there's no way of doing it where it ever repeats. So no matter how big you make that pattern, it never repeats itself. Well, I'll just leave you with that thought. But, in fact, it's a feature of the fact that this universe, well, you see, here's the universe evolving. It'll be something more or less like this. Every now and again it jumps one. It jumps more and more as you go on. It jumps one when the previous set doesn't tile the plane. That one does tile the plane, so it doesn't jump one over here. But it's hard to tell. And, in fact, it's one of these problems for which there is no computational procedure for deciding whether a set of tiles will tile the plane or not. This follows from a theorem due to Robert Berger, was proved some years ago, and what it tells you that the evolution of this universe is not computable. There is no way you could simulate the evolution of this funny universe. However, it's deterministic, and it shows that the notion of determinism is quite different from the notion of computability. And I don't think, you see, philosophers have often worried about determinism. You see, is there a choice in what happens in the future? There are other issues to be considered, and this is one of them. Is it possible to simulate the action of that universe on a computer? And it may not be. There are some toy universes, certainly, for which this is not possible, and this is an example. Well, of course, that's a toy universe. What about the actual universe? Well, the actual universe, what are the laws of physics? We have to know what they are. Well, the laws of physics, I've got them on this slide here. Well, I've left out a detail here and there, but I've really just more or less tried to sort of cover the main physical laws that we know about. And the thing I'm trying to emphasize here is that we really have two kinds of level in which we describe the physical world. Whatever we think about what's really going on, what we do when we describe the world is either describe the world using quantum physics, which is this sort of small level in a sense, atoms, molecules, things like that, sometimes slightly bigger, or the classical level, roughly speaking, big things, where the equations of Newton, Maxwell, that's for behavior of light, and Einstein, when you have large velocities or large gravitational potentials. Now, you see, the quantum level, people think, oh, well, that's where all this fuzzy indeterminacy is and so on. Well, it's not really. You see, the quantum level is governed by this equation known as the Schrödinger equation. I'm using the letter U to describe that activity. And the thing is, it is completely deterministic, as is the classical level. We have determinism here, we have determinism here. But more to the point, for what I want to say, is that we have computability here and computability here. I put a bit of a question mark, well, especially down here. That question mark I don't want you really to worry about. It's there because the physical laws that we understand are laws which depend on continuous parameters and not discrete things, whereas the notion of computability is a notion which applies to discrete systems. So there is actually a bit of a fudge here, but nevertheless people don't normally worry about that. They say, well, you could simulate closely enough by a discrete computation the continuous behavior of these equations, and likewise these ones. And let's say, for the purposes of argument, that that's good enough. Well, what about the probability, what about the indeterminacy in quantum mechanics? Well, that comes about in a different kind of procedure, which is, roughly speaking, when you take a quantum level thing and magnify it up to the classical level. So there's some little thing which happens, and you make a measurement, which means that something you can see or some reasonably big thing happens, and you move from this level to this level. And it's the process of moving from this level to this level that introduces the indeterminacy. And this is the conventional way of treating quantum theory. You have things chugging along here. It's deterministic and computable. Every now and again, it's probabilistic, random. Well, you see, you might think is that what's really going on? Well, I'll say something about that in a moment. But that's what you do when you do quantum theory. Now, I should make a remark about this going from here to here. You see, these are deterministic and computable. These are deterministic and computable, these laws. What about this procedure getting from here to here? Well, the conventional theory treats this going from here to here purely as a random procedure. It's a probabilistic procedure. Now, I didn't really talk about probabilistic procedures when I was talking about computability, but let me just say that you can, in fact, include that in the discussion. And you can bring random elements in, and they don't really make any difference. I mean, it makes technical difference, but the essential point is that you can't really get round the Gödel argument introducing these random ingredients. So this kind of thing, the randomness, is not what I mean by non-computability. What I mean is much more, well, things like that tiling problem over there. Not that, something much more subtle and sophisticated, but something of the nature of that in the sense that it is a mathematical scheme which is not computable and which might be deterministic. I'm not going to say whether I think it is or not, but it could be. Well, I have to say a little bit about quantum theory, I'm afraid. So I've got quantum theory on the transparency here too. Well, there it more or less is. Let me just explain a little about this. You see, this is sort of archetypical quantum mechanical experiment is you have a photon source here and a screen over here and a couple of slits that these photons are supposed to go through. And let me just take a particular point on the screen here, and I'm choosing this carefully so that if I open one of the slits and close the other, it is possible for a photon to get from here and reach that point on the screen. If I close this slit and open the other one, it is also possible for it to get through and reach that point on the screen. But if I open both slits, miraculously, these two alternative things that the photon might do somehow cancel each other out, and it becomes impossible for the photon to reach that point on the screen, if I choose the point carefully. Now, how does one understand that? It's a very mysterious thing, that somehow things that might happen somehow cancel each other out. Well, one understands that by considering that the state of a photon between here and here is neither A, well, it isn't just A and it isn't just B, it's some kind of combination of A and B together. What you have to say is, in a certain sense, the photon goes through both slits at once. And this is a very general principle. If one thing can happen, that's alternative A, or if another thing can happen, that's alternative B, then you have to allow that weighted combinations of these two things can also happen. And that's the sort of thing that happens when the photon goes through from here to here. It does a combination of both things at once. What's strange about this is that these numbers here are not, you might think they're probabilities or something, they're not at all. They are numbers which involve a square root of -1, these funny things called complex numbers, when you can plot them on the plane if you like and so on. Well, I'm not going to worry about the details there, but you do need these funny numbers to describe the way things happen at the quantum level. And you do have to consider that these superpositions of alternatives actually take place. And that's all going along down here. But when you go from here to here, and that's where I've got this letter R coming in, you do something different. That's when you make a measurement, when you magnify something from the quantum to classical levels. Suddenly you take these complex numbers, do what's called squaring their moduli, which means taking the distance from the origin in this diagram and squaring it. The ratio of those two become the relative probabilities of these two alternatives. And this is what the procedure R is. Well, that's more or less quantum theory. You say that's a pretty funny theory. But it is a pretty funny theory. And I think nobody would believe it if it didn't work. And I've just put on this transparency. Well, you see, lots of things. I'm not going to bother you with all these things, except just to say, you see, you might think, well, you see, all these things are great success stories about quantum mechanics. Let me just point to the bottom one here. This is often pointed out. The magnetic moment of the electron, the comparison between theory and experiment. You have all these decimal places here, and they agree to something like 11 places of decimal. It's quite extraordinary. So we have to believe it. Quantum theory really is telling us how the world works. Well, you see, I think people are hypnotized by this extraordinary accuracy, and they say, well, maybe this level is really the whole thing, that all these things are somehow approximations to this level there. And I think that is the normal attitude. So, all right, you see, the idea would be the universe is therefore precisely ruled by quantum mechanical laws. Well, there is a fly in the ointment, or perhaps I should say a cat, which is poor old Schrodinger's cat. Well, you see, this was a thought experiment, I should emphasize. Schrodinger was not somebody who would have done anything to a cat, I'm sure. Here we have a photon, it's a bit like the two-slit thing, coming through here, and here we have a half-silvered mirror. So this photon is to be thought of as both going this way and this way at the same time. That's what happens. That's the way you have to do things in quantum mechanics. This is one of these funny superposed states. The photon is here, first of all, and then it's here plus here at the same time. It's that sort of combination I've got at the top over there. And then you see this part of the photon, well, it goes off somewhere. This part goes through, triggers this device, fires a gun, and kills the poor cat. And you see, if you consider the whole thing as a quantum system, then you have to think that the cat also partakes of this linear composition, this superposition of these two alternatives. Well, Schrodinger brought this up, I think, just to show this is ridiculous, you see. I mean, the cats don't do that. And he didn't, I think, he was allowed to say, of course, it's his equation, so he's allowed to say that he didn't believe it at this level. Although I think other people didn't feel that they could say that somehow. They think, well, somehow you've got to understand how it really applies at this level. Well, I want to say, I'm not going to go into all these arguments. There are many, many different viewpoints about the cat. All I'm going to say is that my own point of view is that this picture needs some modification, and here's the modification. That the usual procedure of going from here to here is approximate. Well, really, the whole thing is approximate, if you like. These two levels are approximations to some theory we don't yet have. And this theory we don't yet have will involve some procedure which replaces this conventional probabilistic procedure. What kind of procedure it is, we don't know. But it's where I'm saying the missing non-computability comes in. And I've called this OR, that means objective reduction. The R here means reduction. People say the collapse of the wave function or the reduction of the state vector. OR means objective reduction. It's something which really happens in the physical world. And it's an appropriate acronym because it says OR. The cat is either dead or alive. See? So, whoops, I mustn't lose that. The whole theory has gone onto the floor. Thank you. So you see, when it gets to some stage, somewhere between here and here, something new comes in, according to what I'm saying, and the cat is either dead or alive. I think Schrodinger would have agreed with that, rather than agreeing with his equation. Well, we don't quite know what he would think because he's not here. But, so I can say whatever I like, he would have thought. Well, we've seen... Oh, these things are terrible, aren't they? Yes. The gremlins. We've seen one good theory, which is quantum mechanics. I want to show you another good theory. This is Einstein's general relativity. And it's actually quite a remarkable thing. As with quantum mechanics, one has a very beautiful mathematical scheme. And I think that's one of the impressive things about physics, is how well mathematics can be used to describe the physical world and to extraordinary accuracy. Now here we have another theory. It was formulated in 1915, not really motivated by observational need, but some kind of aesthetic, geometrical, physical desiderata. Now I'm not going to go into all this, except to say that now we have, after many years of having sort of rather miserable kind of tests, not that miserable, not too bad, but not terribly impressive from the point of view of physics, and certainly not comparing with quantum mechanics. But now we have, well, a Nobel Prize was won by Hulse Taylor in 1993 for a very remarkable series of observations and interpretation of these observations. This is a binary neutron star going around each other way off somewhere, wherever that is, 30,000 light years away. Signals coming from one of them, which happens to be a pulsar, little blips come to the Earth. And this system can be modeled, well, first of all, using the Newtonian orbits. That's really now, I'm considering that as part of Einstein's theory. It's an approximate part of Einstein's theory. Corrections to that, and finally the corrections due to the emission of gravitational waves. And in a certain sense, you can say this theory is now confirmed, at least in this object, to something like 1 part in 10 to the 14. How do you get that? Well, you see, over a period of 20 years when this thing has been observed, these blips which come from the pulsar can be timed to the kind of accuracy that over a period of 20 years you get something like 14 figures. So that's a bit better than the 11 or 12 that one sees in quantum mechanics. So what I'm trying to say is that good that quantum mechanics is, and it is, it's incredibly good, it's not any better than general relativity. So it seems that we ought to consider the principles of general relativity and apply them to the cat. Well, you might think, what's a cat got to do with that? Well, the cat, you see, well, I'll put the cat back. It'll probably fall on the floor again, but the two positions of the cat, this is, all right, let's say the cat's standing up or falling over. It doesn't have to be as gross as that. Will each have a gravitational field. And those gravitational fields will influence the space-time. And so what I'm going to say is that perhaps something goes wrong with the superposition principle when it applies to significantly differing space-time geometries. So instead of having these superpositions, which you have with the two geometries, you get one or the other. And that is the sort of thing I'm saying takes over. And you have to really look at this quite carefully to see what the general relativity has to say about quantum mechanics. It's usually, you see, people think of it the other way around. They say, what does quantum mechanics have to say about modifying general relativity at one level? I'm saying general relativity will have its influence back on quantum mechanics. And to cut a long story reasonably short, I just want to show you what I say happens. I've replaced the cat here by a lump. I think perhaps that's a bit more humane. I still have this photon, which is both being reflected and transmitted. The transmitted part triggers a device, and all it does is it moves a lump from one place to another. And then what I want to say is that this superposition of these two lump positions, which is what quantum mechanics tells us ought to happen, that superposition, perhaps I should put quantum mechanics back over here, like the one we had here, you see, that superposition is unstable, and that it decays in a lifetime. It's a bit like an unstable particle or uranium nucleus or something. After a certain time, it goes into something else. And so what I'm saying is that the superposed state, after a certain time, goes into one or the other. And the suggestion is that you consider the energy it would take to displace one instance of the lump away from the gravitational field of the other. That gives you an energy. Then you take the reciprocal of that. Well, you take this Planck's constant thing, Planck's constant over 2 pi, divided by this energy, and that gives you a time, and that time is the decay time. Now this follows certain ideas also introduced particularly by Diossi. I won't go into these other suggestions. There are many suggestions that have been put forward in recent years for modifications of quantum mechanics. This particular one is somewhat in line with some others, not precisely the same perhaps. Let me perhaps leave that there. If it quite fits on. There we are. Doesn't quite. And give you just a few figures here. these are just to show you what happens. You see, here's the lump in one position or in another position, and I want to say that this decays, this superposition decays into one or the other. And if this were a nucleon, say a proton, then it would take a few million years. If it were a water speck, according to the scheme, it would, well, I've given some figures here. 10 to the minus 5 centimeters in radius, it would take a few hours. Micron, a 20th of a second. 10 to the minus 3 centimeters, a millionth of a second. Now, that gives you some idea of the sort of level at which this new kind of physics would start coming in. Now, you have to be a little careful of this because it's, in practice, very, very difficult to keep a lump isolated. And what it would normally do would be to be accompanied by some environment. I've indicated that by lots of these dots here, you see. And these all move around as well as the lump. So you have to take all that into account. And the thing is, usually the environment is all random, and so that whatever happens here is effectively random. And this is why I'm saying that this new type of scheme would really agree to a very high degree of approximation with the normal procedures that one uses in quantum mechanics. However, if you had a situation which was very carefully isolated, if you could keep that lump isolated from its surroundings in a very, very careful way, then you might be able to see different effects, and I would argue that you would ultimately be able to see non-computable effects. So this is what somehow the brain would have to be making use of. Now that's a pretty tall order, you might say. It needs new physics, and it has to find the right circumstance for that new physics to be relevant. Well, that's where I'm saying we have to go. Well, all right, what about brains? Here's a picture of a brain, more or less. You see you've got these neurons going along and signals going along the neurons, and every now and again a signal goes over onto the next neuron. And it does this through this synapse. It has to jump a little gap to go onto the next one. Now the thing is that, well, first of all, you could imitate that kind of thing with a computer, and that's the sort of picture people do have. But also you have to worry about the fact that these strengths of synapses tend to change. They're not fixed for all time. But you see, if the way in which they change is again something you could program onto a computer, then, well, you could make your computer do that too. And that's the sort of thing people do in what are called artificial neural networks. It's some attempt to imitate what the brain might be doing, where these synaptic strengths do change from time to time, but the way in which that strength change is governed is again some kind of computational procedure. But what I want to say is, all right, that's fine as far as it goes, but neurons are much more complicated things than that. They are cells, and cells behave in complicated ways. Well, you see, what about a one-celled animal? Here I have a paramecium, which can swim towards its food, it can retreat from danger, it can negotiate obstacles, it can even apparently learn by experience. So can an amoeba. They can do that kind of thing. The question is, how do they do it? Well, you see, they certainly don't do it using neurons because they're just one cell. And if they're not a neuron themselves, which indeed they're not, they haven't got a nervous system. But they have other kinds of structure which might serve instead. They have what's called a cytoskeleton. Now, cytoskeleton consists of various things. In particular, it consists of things called microtubules. I want to say something about microtubules. Well, first of all, the things that the paramecium swims with are these little hairs here, which are made up out of little tubes. These little tubes are called microtubules. Now, in fact, when the amoeba moves, it sticks out these pseudopods, and these are also governed by microtubules. There are all sorts of other things. Well, there's a sort of a center that they have called the centriole, and one of the things that microtubules do is in mitosis, that's in cell division, they sort of drag the chromosomes away, and it's all kind of highly organized. If you've ever seen this kind of thing going on, you see how highly organized this cell division is. And it's the microtubules and maybe this control center, which is also made out of microtubules and other related substances which seem to control the way the cell behaves. So it's really very complicated. Now, what's that got to do with brains? Well, you see, the axons and the dendrites and so on, have got microtubules running down them. And, well, here's a picture of a microtubule. I think I'll show you that perhaps on the other one. Let's see. Here's a microtubule. It's made up out of these little proteins known as tubulin, which consists of two little bits here, and there's an electron in there which can move up or down, and depending on where it is, it goes into one state or another. And Stuart Hameroff in particular has argued that these things act as little computers, or cellular automata, where what one of these little tubulin dimers, as they're called, does, which of these two states it's in, is dependent upon what its neighbors are doing. And this enables complicated messages to go down these microtubules. Well, it's quite possible, and if indeed that's what's going on, then these microtubules could influence the strengths of these synaptic connections. Well, they do all sorts of things. One thing they do is actually transport chemicals along. I have a video which I hope we can see in a few minutes, which shows you pictures of microtubules transporting substances along them. It's really quite remarkable to watch. And they do this, and in particular the neurotransmitter chemicals which are responsible for the signal going from one place to another are transported along by the microtubule. So the strength, the concentrations here would certainly be influenced, or could be influenced by microtubules. There are other ways they could affect the strength of a synapse, for example by this substance here is actin, which is what makes muscles contract, and that could influence this dendritic spine thing here and change the strength of the synapse. So that's the sorts of things they can do. I just want to make some remarks about the organization of microtubules, just to show you that they are very tightly organized structures. I was always rather struck by the fact that there are 13 of these rows going along, and that seems to be a uniform thing. Microtubules, at least in most mammals, there are always 13 of them. And 13 you might think is a funny number after all. What's so good about 13? Well, I'll tell you something else. Suppose you look down the microtubule. This is supposed to be what it would look like if you could look down one. They actually sort of spiral around. I've got this indicated here. If you follow them around, you find that when you get back to the same column, well, this one is 8 down, and if you go the other way around, it's 5 down. And what's so special about these numbers, 13, 5, and 8? Well, they're what's known as Fibonacci numbers. Here I've taken a microtubule, I've slit it down and opened it out, and you can see you've got these 8s, 5s, and 13s. The Fibonacci numbers, you start with 1 and 1, you add them up together, you get 2, you add these 2, you get that, you add those 2, you get that, add those 2, you get that, and so on. You see Fibonacci numbers in plants quite often. It's something which seems to be very important in the structure of biological systems. I don't know whether that's anything to do with the microtubules, but it seems to be also the case that microtubules are organized in this very precise kind of way. I'm really just trying to show you that they are tightly organized structures. Just as amusement, or perhaps something more serious, I want to show you something else, which is things like this. Well, you may have heard of buckyballs. Those are carbon molecules which form these shapes which look like soccer balls and other things more complicated. They're called fullerenes. This is something different. These are actually, I think they're a sort of polypeptide or something. They are biological things. They're not made of just carbon. They're much bigger than these fullerenes. But you notice they have this highly organized geometrical structure. And where do they sit? Well, they seem to sit right here at the ends of these axons. I don't know what they're doing, but I just want to try and stress the fact that there is a tight kind of organization going on here, and it's quite possible that these things and the microtubules themselves could support some kind of quantum activity. Now, this is what one would really need for the kinds of arguments that I'm putting forward here to hold. What I need, you see, is that there should be quantum activity maybe even something like what people call quantum computers, where you see not just Stuart Hameroff's activities here, where you have this thing going on, but you have at least at some stage and for a bit, I don't know how long, you would have these superpositions taking place as well. And then at a certain point, these superpositions would have to, when enough movement takes place, when these tubulins move enough, according to the sort of criterion which I've been trying to say, this picture here, when enough movement takes place, then the new theory comes in, and you have to go beyond quantum mechanics or something. Well, you might say this is far-fetched, because the brain is, after all, a sort of warm, chaotic kind of structure, which may not be, at first sight, conducive to the preserving of large-scale kinds of quantum activities. Well, okay, maybe it's hard. I'm just saying that you've got to find it somehow. And the most promising kind of areas I've seen are in these microtubules, possibly in things like this. And what you would need would be some kind of large-scale activity taking place maybe within the tubes, which is appropriately shielded from the outside. You see, you need to have something which is kept from disturbing the environment. That's the hard thing. And which now and again starts to influence the activities of these microtubules. And at a certain point, the new physics actually comes in to make a difference. So that's the kind of general picture I'm saying. Something like that, I'm saying, has to be there in order to get the non-computability that you need. You see, there are speculative points all the way along, because you need it in the physics. You need that physics to be relevant to the brain. You have to have quantum theory to be relevant for the brain, and not only that, you have to have a place for this kind of activity. Well, you can actually even start to make some kind of numerical assessment of the amount of mass that's moved and compare that with how long it takes for conscious events to take place and so on. And it's, well, it doesn't fit too badly. The problem is really to get this kind of isolation that you would need, and that, of course, is a big problem. Well, let me just finish by showing you a picture. I'm finishing by going to show the video, but let me put this on first, which is just, I'll just leave that there, I think. You see, this is a sort of summary of what I imagine. What I've been talking about is, first of all, this. You see, this is how we perceive mathematics. The Platonic world is the world of absolutes, in particular mathematical absolutes, and how you know about mathematical truth, which is this arrow here. I've also been talking about quantum theory and general relativity and maybe some new physics we don't know yet, which would be how the physical world seems to be governed by these mathematical principles. And I'm talking also about this arrow, which is how our mental selves seem to emerge once one has the right kind of physical structure. But I'm trying to say with this diagram here that we're not going to understand any one of these things until somehow we can make sense of the picture of a whole. All right, let's see if we can get the video going. The video is just to show you some of the things that microtubules can do. And they're really remarkably clever things. So I hope this works. I've never actually shown a video before in a talk, so oh, very good. Well, Bill Andrew gets all the credit.
The dramatic improvements in digital image processing techniques have enabled ever clearer views of the movement of vesicles along microtubules. Vesicles can move in both directions along a single microtubule. Images such as these permit kinetic studies of vesicular movements.
So it looks a bit like a highway system. And they're transporting these chemical substances from one place to another.
This speeded up version emphasizes the extent of vesicular transport that can take place in all living cells. dynein is attached. This was the first demonstration of force production by a purified dynein. The dynein was isolated from the outer arms of sea urchin sperm tails, while the tubulin for these microtubules was isolated from calf brains. The average speed of these gliding movements is about 3.5 microns per second.
So apparently they move under certain circumstances.
A subunit of the dynein molecule, the beta IC1 subunit of the sea urchin outer arm dynein, can also support the gliding of microtubules on glass cover slips. This large freshwater amoeba was found in the investigator's fish tank. Computer-assisted image processing techniques, coupled to differential interference contrast microscopy, permits the organelle movement to be observed quite clearly in this real-time recording of a living cell. Note the bidirectional movement of organelles in these flat cytoplasmic strands. The velocities can be as high as 25 microns per second. Electron microscopic studies have demonstrated that the particles are associated with microtubules.
Okay, well, thank you, Bill. All right, well, thank you very much. That's it.
So we'll take our speaker briefly to the two overflow rooms and then bring him back here for your questions and his answers. You will be able to hear the questions asked in the other room.
referring to. I mean, when people talk about artificial intelligence or something, he claims that his scheme is different from that. I'm not clear that it is really different. He has certain ideas where he does incorporate sort of natural selection I mean, his sort of neuron things make choices on the basis of some kind of natural selection principle. But I don't see why that isn't already incorporated in the types of procedure that are used in what might be called bottom-up programming in artificial intelligence. So I don't really quite see why it is different. It's a specific type of method he uses. And since he does have computers which do what he says, they are, in my sense, computational. So the test for whether a system is computational, in my sense, is whether you could put it on a computer. And since he does put his on a computer, it is, in my sense, computational. I mean, they could involve random elements, but then I'm including that in what I'm saying too. You could say a computer with a randomizer, but my arguments are equally aimed at computers with randomizers as they are at computers without randomizers. So it wouldn't get round the problems that I'm talking about, the Gödel type difficulties. Could you write a program that you hand to a person to implement? Yes. I don't see why that makes... Yes, I'm sorry. Well, as far as I understand it, you were suggesting you could have a computation that is not actually carried out by a computer, but is implemented by a human being, as in Searle's Chinese room. Now, that is still a computation. So I'm not saying that human beings can't do computations. I'm only saying that consciousness is controlled by something different. It's not computational. It is, I mean, you can do those things without thinking, if you like. I mean, you could do it consciously if you want to. But I'm not saying that it's not a computation just because a human being does it. I'm saying that the things which underlie our conscious actions, our conscious thoughts, behavior, involve non-computational elements. So that doesn't go against what you're saying. Let's see if I can understand what you're saying. I mean, you're asking me about if quantum mechanics and general relativity are both right. Well, I'm only saying they're both right in a limiting sense. They're not exactly right because each one is modified by the other. Most people would agree that general relativity can't be quite right. It has to be, under certain circumstances, modified by the rules of quantum mechanics. What I'm saying is, in addition, quantum mechanics can't be quite right. It has to be modified by the principles underlying general relativity. So we need some...
If you give us a nice program,
yeah.
How we can find out whether that intersection is proven, if you gave a biological model, or where we could look for that, the synapse.
Yeah, you're saying I gave a biological model. Well, first of all, it's physics. I mean, one has to tackle that first, because we don't even have the right theory yet. All I'm saying is that there is a level, one can start to estimate the level at which the new theory will become relevant. And then you have to ask, is that level of relevance in the brain? And so what I was trying to say is that the best hope for that is in things like microtubules, possibly these clathrin molecules, where you can possibly support large-scale quantum coherent activity, which would, so you have a big quantum state. It starts to move things around, big in the sense that, well, it's not big in the sense of moving that much around, but big in...
You have a quantum state that's still measurable by us, but big enough for us to see.
Well, it'd be a lot smaller than that. Once you see it, it's too late. It would have to be small activities taking place within the brain. I mean, it wouldn't have to be within the brain. I'm saying you ought to be able to, if you're clever enough, build some physical device which would exhibit this new type of physics. But what I'm saying is that somehow the brain, biological systems, certain biological systems have been that clever already and have found the right framework for this new type of physics actually to enter.
Sir, I do apologize, but I think we have to take Dr. Penrose. So we have yet another overflow room, and then he has to go back to the main audience. Then he is also going to sign his autograph and copies of his book for those of you who are wise enough to buy them. So, thank you. So we have time for a few questions.
Mr. Penrose, your book is called Shadows of the Mind, but this evening you've referred repeatedly to the brain. Do you assume that the brain and the mind are identical? And if you do, could you briefly defend that assumption?
You're saying I refer to, the title of the book is Shadows of the Mind, whereas in my talk I was referring to the brain, and am I regarding the brain and the mind as identical? I think I wasn't saying that. In fact, that slide I had just at the end perhaps illustrates more what I feel. That mental phenomena are something which have to be studied in some way, and maybe in a way which could be described as scientific. But I was having that sort of the mental world is not sort of sitting in the physical world, in a sense, in that picture. So I wasn't saying that I think of them as the same. I think thinking of the mind and the brain as the same would be not appropriate. But I don't know what the mind is, but on the other hand, that is what we are most immediately aware of. So it's a sort of paradox there. Somehow what we're most immediately aware of is in a sense what we know least about. But I think we again, as in that picture, I'm saying we have to understand what's going on in terms of the activity which is taking place in the physical world, and likewise the physical world in terms of what's going on in the mathematical world. But then the mathematical world, in some sense, there's meant to be a kind of paradox in that picture, which is which is deliberate, because I think that there are deep issues there that we're very far from understanding. Perhaps that will.
In the design of complex systems, one of the most valuable design strategies is you introduce levels where the details of the higher levels become progressively more isolated from the details of the lower levels. So you have like unreliable logic elements, and you introduce your error correcting codes, and then you keep it on to the next. From your talk, I understand that you would reject this view for consciousness. I mean, that the lowest level details percolate right up to the highest levels. Is that accurate?
Yes. I have to repeat the question. The question has to do with levels where one talks about activity at one level, and then again at a higher level, and a higher level, and a higher level, and often discussions of sort of artificial intelligence discussions of mental qualities are talked about in these terms. We might think of emergent properties which come about at a bigger level, and then something else which emerges out of that, and so on. That's certainly not my view, because all these things are still computational. So although it might be useful sometimes to think in terms of levels, and it often is, it certainly is in physical systems, where certain types of concepts are appropriate at one level which may not be appropriate at another level. For example, even things like temperature which refer to systems with many degrees of freedom, whereas when you're talking about an individual particle, it's not an appropriate concept. So you certainly have concepts which are, in physics, say, which come up at different levels. But what I'm trying to say is, in a sense, cutting across all this, I'm trying to say that there are certain things which aren't restricted to level. Let me give you an example. In physics, again, the law of conservation of energy is something which carries right through from the lowest level right up to every level. I mean, it applies to an athlete who's performing, pole vaults or whatever it happens to be. And the law of conservation of energy applies just as much at that level as it does at the level of individual particles. Now, there are other things which aren't like that. It does depend on what level it comes in. And what I'm saying is that the non-computability issue is not a level thing. That is to say, you couldn't have it at the higher level if you didn't already have it at the lowest level. So that's really the argument, is it's not simply a matter of levels.
Yes, if your consciousness arises from quantum non-computation of quantum processes and microcubics, does it even make sense to think that there is a reality which consciousness of different people or animals represents to varying degrees of accuracy? Is one consciousness more right in its representation of this reality than some other type of consciousness?
I want to see if I get your question right. You're asking me, in the representation of reality, whether one consciousness could be more correct than another. I don't see why not, but I mean, certainly people can be. I'm not sure I'm answering your question, but certainly people could think the Earth was flat or something, and somebody else could think it was round, and the person who thought it was round would be more correct than one who thought it was flat. But I'm not sure that's what you're asking me, is it? I mean, I'm certainly not saying I'm not a relativist in the sense that each viewpoint is equally to be respected. Well, viewpoints are to be respected. It doesn't mean that they're equally correct. I think there is a difference, and that there is a correctness. There is something out there which is in a sense true, and that one may grope towards that truth. Some people may be better at groping towards the truth than others, or some people may be luckier, or some people some time might be better and other times worse, and so on. But I'm not saying that they're all equivalent. I don't know if is that your question? Have I answered you?
Yes. So the quantum physicist will eventually have a picture of reality.
Aha. Okay. I see.
Reflects,
Yes.
An objective truth, whereas your average animal or human beings will not.
I wouldn't put it like that. I thought you were going to address the question of objectivity in quantum mechanics. I mean, quantum mechanics, it has this reputation, and certainly some people look at quantum mechanics as rather saying, oh, well, it's all in the mind, and there isn't really a reality out there at the quantum level. And I'm afraid Niels Bohr rather set people thinking along those lines, I think, to some degree. No, I'm much more a realist in saying that there is an actuality out there, which may be described in different ways, which may or may not be equivalent. We don't know what that way is. But I think there was a slightly different edge to your question, which is that somehow quantum physicists were supposed to be more closer to the truth than others. I would hate to say that, no.
I think we'll have to take Dr. Penrose back to the main audience room. Thank you very much. Thank you all for waiting. So we're now open for questions from this room.
Which together would help to explain consciousness. Do you see a place for
Do I repeat the questions here too? The question was, some theorists concerned with consciousness believe that nonlinear dynamics connected with quantum mechanics are, I don't know what is relevant to the issue of consciousness or whether it's explaining what consciousness is. I do address the issue of chaos. I mean, there's separate points here. One is chaos, which means, I mean, normally one's talking about classical systems, where one has a behavior which depends very critically on the initial state. And the example of the weather is always is brought up here, that you can make maybe you can make your computer work out how some system evolves, but you have to be very careful about how you set that up in the first place. If you get it even very, very tiny bit wrong, then the ultimate behavior will be completely different. You were also asking me about quantum systems, and there is a subject known as quantum chaos, which is a subject which I find puzzling because chaos is something which occurs only in nonlinear systems, whereas quantum theory is a linear system. However, there is such a subject, and what it refers to, I think, is when you apply quantum mechanics to these classical systems which are chaotic. Now, your really question is do I believe this has anything to do with the brain or mentality or consciousness? I don't know whether it has anything to do with it. It's certainly not my view as to what's going on, because chaotic systems, they are actually considered in Shadows of the Mind. I talk about them. They are still computational systems. The ordinary chaotic system, in the ordinary sense, is still computational. In fact, people exhibit these wonderful chaotic pictures of chaos and all that stuff. Where are they made? They're made on a computer, after all. So they are, they are computational systems in my sense. Now, of course, they may depend critically on this initial state. And you may say, well, if you want your robot to behave like this human being, that robot has got to have the right initial state. But of course, you're not saying that. You just want a robot to behave like a human being. I mean, that's what the AI point of view would be. So I don't quite see why it's a critical issue. I mean, it's not as though you want to simulate the weather for the purposes of making a robot behave like a human being. Simulating a weather would be just as good. It doesn't have to be the actual one. So I don't quite see why chaos is a critical issue here. But it does raise some points, and I may have dismissed it a little bit too glibly here. But then I'm not sure whether quantum chaos, well, let me leave the question at that point. I think maybe I've said enough about it.
I'm curious what originally brought you to this point of view, the one you described as seeing consciousness will not be.
Yes. What brought me to the view that's a point of view C on my transparency, the first transparency? Well, actually, I think I must have held that view for a long time before I ever contemplated writing anything about it. Really, after I learned about Gödel's theorem, because it seemed to me that the interpretation of Gödel's theorem that seemed to me to be a clear interpretation, tells us that when we understand things in mathematics, we are not doing things which are of a computational nature. I didn't worry about it particularly. It's just I think in the back of my mind I'd had that view. And I had that, I suppose, more or less ever since I was a graduate student. But it was only when I think I saw a television program in which Marvin Minsky and Edward Fredkin were making some very extreme remarks about these computers which would, in a few seconds, had communicated more information than the whole of humanity ever since the dawn of time. It seemed to me that, okay, from their point of view, maybe it's logical, but I hadn't seen the point of view which I seemed to have held for all these years expressed, and that was why I wrote The Emperor's New Mind, basically, because it was a viewpoint which I felt ought to be expressed. But then the separate point is, where is it in physics? Because normal physics, one doesn't see it. And quite for separate reasons, quite nothing to do with this whatsoever, I've certainly for a long time felt that quantum theory needed at some point, some modification. I mean, to do with Schrödinger's cat and things like that. And therefore, it seemed to me that was the only plausible place where this non-computational thing, which I had already believed must be there somewhere, would come in. So I think that answers your question, I hope.
Do you not underrate the selective advantage of mathematics? The size of the human brain and its ability to do mathematics is a wooing advantage. And a man called Miller has put forward this in a book called The Red Queen.
Oh, yeah.
The innovation and a lot of skills which seem unnecessarily complicated have arisen from intra-specific, intra-human competition.
The question is, am I underrating the value of mathematics from the point of view of natural selection? And you mentioned a book, which I've forgotten what it was now. The Red Queen by
Ridley.
Ridley. Anyway, I don't know the book, so I can't answer that. But what I was referring to was really specifically doing mathematics. In fact, the cartoon I gave there is a bit more. I mean, I could just show it here, but it's the point of it was not quite. I couldn't perhaps make it clear in the discussion here. It has to do with a possibility that there might be some computational procedure. This is the thing Gödel actually suggested as a let-out for his theorem. I mean, he considered that there might be some what he called a theorem-proving machine which could generate the number theoretic propositions that are accessible to human beings, but which we could not know was actually right. And he said that this is a logical possibility. He didn't believe it. I mean, I think he believed more in point of view D than certainly didn't believe A. But he was regarding this as a logical possibility. But how would such an algorithm come about, you see? And it seems to me that such a thing would have to be so sophisticated that it's even beyond present-day mathematicians. And how could that have come about in the sort of environment in which our ancestors evolved? And it seems to me that is too far-fetched, really, to believe. So that cartoon was really more specific to that. What I am saying is that the ability to understand things, generally, which is not really specifically mathematics, but in mathematics it's rather more refined than in other areas. It's just the ability to reason and to understand and have insights and so on, which is, I would say, something which is indeed something which was selected for. And it's just in mathematics one has a particular, one uses it in particular ways, that's all. I'm not saying it's specific to mathematics. That was a type of argument I was...
The only point this argument is making is that
yes.
the human brain does seem to be unnecessarily complicated.
Unnecessarily complicated.
The idea is that
I don't know.
what we are competing against is one another.
You're talking about competition between individuals.
For wooing advantage, for courting advantage.
Yes, well, you mean it's like, you say that we're unnecessarily complicated. It's a bit like the moose with its great horns and so on, and that somehow it's done this by bashing them against the other ones, and we are doing it bashing our brains against each other and so on, and somehow evolved because of that kind of competition. That's what you're suggesting?
Plus, innovation is attractive.
It's conceivable. I think it's more likely that probably it was against the animals that we were that somehow. But it's a possibility. I'm not sure I see that as a selective advantage, but I suppose it could be. Yeah, it's possible.
Yeah, I think Dr. Penrose is now on double overtime, so I think we can allow one more question. Yes. Speak up.
Yes, the question is, do my ideas go anywhere towards explaining intuitive judgments? Of this? I didn't actually talk specifically about, well, I see intuitive judgments, it depends what one means by that, of course. And in Gödel's discussion, he actually talks about mathematical intuition rather than mathematical understanding or mathematical insight. I think insight is probably a good word because I think people tend to think of intuition as something, you know, it's just a sort of guess which turns out to be right by some magic. I don't mean that kind of thing at all. I'm talking about insight really means you have some kind of deep understanding as to what's going on and intuition in that sense. So I think we're a long way from really explaining any of these things. I'm certainly not talking about inspiration in the sense of ideas which seem to come from where, who knows. Mainly because, not because I think they're things that computers can do. I don't think they're things that computers can do, but it's hard to argue about them, that's all. So the reason I concentrated on understanding, or perhaps insight, is that at least one can make a clear statement about that kind of activity. One can say that the Gödel-type arguments seem to suggest that that isn't something that can be done by computers. And it's very possible that all sorts of other things aren't either. And I would, the thing that one calls intuition, I would say, indeed, is something that cannot be done by a computer. But it's not explaining. See, my arguments are all terribly negative. All I'm saying is that computers can't do it. Computers as we know them now, what we understand by a computer, which means the Turing machine, basically. And I'm saying that that cannot do it. But that some kind of object constructed in the right way, and the human brain would be an example of such, seems to be capable of doing these things. Now, how it does it is way beyond anything I've said here. My arguments are entirely on the negative side. Well, and there's a little bit positive, I hope, in some places, but negative in the sense that it's something that is not purely of a computational character. It's something which requires something else. And so I'm led along, well, what else could it be, and where could that be, and so on. But it'll be a long, long time before we have any real understanding what's really going on, whatever it is that underlies actual intuitions, insights, and so on. I think that's something way beyond anything I've said today.
President David Strangway has the pleasant task of thanking our speaker.
It's a great pleasure to thank the speaker. At the beginning, Dr. Cairns made reference to the fact that during the series of the Vancouver Institute lectures, that it was a wonderful tour de force on interdisciplinarity. After listening to the lecture tonight, I came to the conclusion you didn't need to come to all of the lectures for interdisciplinarity, just one. And then I began to reflect a little bit, thinking of the structure of our institution. Which department would he fit in? And I had quite a lot of difficulty trying to decide, mathematics, obvious, physics, obviously, computer science, obviously, perhaps psychiatry, I'm not quite sure. That gets at least 2 different faculties, and I even contemplated about the possibility of values and judgments, and perhaps somehow that would get into religious studies, but I could not fit him into political science under any circumstances. Anyway, ladies and gentlemen, it's my great pleasure to express appreciation for a really wonderful lecture that brings together things that we all think about and reflect on, but has done them in such a marvelously insightful way that we really do thank you very much. Thank you, Dr. Penrose.